Hi there, this is lecture 8 on section 2.8, the derivative as a function. So if you notice when we did the practice problems from the last section, I was asking you to do more than 1 point. I wanted to know what is the instantaneous rate of change for this function at more than 1 point. And each time you had to start over and take a whole limit for each one. And that's a lot of work. So we want to think of, can we go back to this process and can we do this in a way that we could write our limit in general for any value, any point that we want for any a. And that way we can get a formula or a function for the derivative and be able to plug in different points to find the derivative at different points. So let's go back to what we know. So we're going to go back to kind of what you did with our example where we had x squared plus 3. So our function here is the x squared plus 3. And we were looking at the, particularly what happened at 2 comma 7, right? So what was the instantaneous rate of change at 2? And we calculated a bunch of slopes, right? And then from there, we generalized what was happening so that we could get a formula. So let's go and do that, but let's tweak that a little bit. So the first one we did was we said, okay, when x was 2 and x was 5, we took those 2 points. Then our slope was f of 5 minus f of 2. Now, instead of putting the 5 and the 2 in there, and I'm going to put them in a second, but instead of doing that, so let's write them down first. Hold on 1 second. Let me backtrack. Let's write them in first so that we can see it. And 5 minus 2 on the bottom, okay? But now instead of doing that, 5 minus 2 is 3. So I'm going to put the 3 on the bottom. And what I want to do is I eventually want to take out the 2. And I've got too many numbers that are changing. So what I'm going to do is I'm going to relate the 5 in terms of 2. So 5 was 2 plus 3 minus f of 2. Okay, so we're going to do everything in relation to 2 and see what happens. So our next one was x equals 2 and x equals 4. If we do the same thing here, this becomes f of 4 minus f of 2 over 4 minus 2. So we get a 2 on the bottom. And now, instead of writing 4, I'm going to write it as 2 plus 2 minus f of 2. And then next we had x equals 2 and x equals 3. So we had the slope was f of 3 minus f of 2 over 3 minus 2. And that left us with a 1 underneath. And f of 3 we're now going to write as 2 plus 1 minus f of 2. And then we had one more, right? So let's go with x equals 2 and x equals 2.5. So our slope was f of 2.5 minus f of 2 all over 2.5 minus 2. And that'll give us 0.5 in the denominator. And our 2.5 we're going to write as 2 plus 0.5 minus f of 2. And then we're going to see what happens now. So take a look at these, okay? So first of all, what I want to be able to do, this was at the point x equals 2, and I want to take that 2 out of the equation. So I want to make that my x. So all of these 2's, oops, not that one. All of these 2's are going to become x's. So our 2's are going to become x's, okay? And then I want you to see the pattern. Remember that with our, previously, we were looking for a number that was changing each time. And take a look, these two actually change at the same time. And they're getting closer and closer to something. Now, in the last one, those numbers were getting closer and closer to 2, right? We were moving our points, our second point, our 5, 4, 3, 2.5, closer and closer to 2. So we took the limit as x went to 2. But this time, what's happening is I'm looking at the distance between those 2 points. And those are getting closer and closer together. So notice that my denominators are getting smaller and smaller. So closer and closer to 0. Now, if I've already used x, I can't use the letter x here. So what we do is we use our h for our changing value. So if we make that substitution here, then we get this limit definition of the derivative. So what we get is we have f of, now the 2 became the x, so that's an x, and the 0.5 is becoming the h because that's the number that's changing every time, minus f of, the 2 is an x, and on the bottom that 0.5 is changing every time, so that's my h, okay? And this, we are letting the limit, and we're letting that h is the one that's changing, and it's going closer and closer to 0. And this is going to give us the derivative as a function, so f prime at x. Okay, so this is what we mean as the limit definition of the derivative, right? So that's how we're going to calculate our limits. So now when you look at example 4, we're going to go ahead and do this once in general for our function, and then I can plug in all these values at the end, okay? And it can be quicker and shorter. I don't have to do 3 limits. So let's try to execute that. So let's start by, every time I'm going to start with good notation, so f prime of x, and I'm going to start by writing out the limit definition. So the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, something we want to be careful about. This notation right here, right? What's in the parentheses means that's what should be where the variable is, right? So when you have f of 2, that means you put a 2 wherever you see an x. So when I see f of x plus h, that means I put an x plus h wherever I see an x. So that means this is going to be the limit as h goes to 0 of, now f of x plus h means that I'm going to take my f of x. It has one x value. I'm going to replace that x value with an x plus h. And I'm going to put parentheses around it so I don't mess anything up, because the x and the h are married. They're tied together. Minus 3. Okay, so that's my f of x minus h, plus h. Minus, then I want the function by itself. So I'm going to, again, put the 2x minus 3 in, but with an x this time, and I'm going to keep it in parentheses. All over h. Okay, so the purple part is my f of x plus h, and the blue is my f of x. Okay, from here, we're going to distribute and simplify. So this becomes the limit as h goes to 0 of 2x plus 2h minus 3 minus 2x plus 3. Oops, not h. All over h. And now what should happen? Because if we had tried evaluating our limit, we would have gotten 0 over 0. So that h in the bottom, I need to cancel. So everything in the numerator that does not have an h in it should cancel out. So this 2x and this negative 2x cancel, this negative 3 and this positive 3 cancel. And I'm left with the limit as h goes to 0 of 2h all over h. Now I try to cancel out that h, and I can do that. And so this is the limit as h goes to 0 of 2. And I don't have any h's, so I don't have to plug them in anywhere. I just get 2. And so f prime of x is equal to 2 as a function. Okay. Now, is it odd that that's just a solid number? Well, no, and we'll talk about that later. But it means that f prime of 1, f prime of 2, and f prime of 0 are all the same value because there's nowhere for me to plug that in. So that means that I can just state that f prime of 1 is 2, f prime of 2 is 2, and f prime of 0 is 2. Okay. Now, if I had x's in my derivative, then I would go ahead and plug those numbers in and get a different value. Okay. And that's it for our lecture.